So we are back in our Visual Studio. Welcome to the coding section of Object Detection application. I have created here a console application called Object Detection and installed in it the OpenCV for.Windows package and imported the two namespaces, the OpenCV and the OpenCV.dnn in our program class. We have here at the top a string array of the object names that we are interested in. There are 20 of them. The model we are going to be using was trained with image sets containing these objects. Then we define the Caffe framework trained model and the config file paths here. And they are the mobile net ssd underscore deploy.prototext. And the model file is mobile net ssd underscore deploy.caffe model. Also, we have here our test image path. And on line 23, I have written a code line to select one of possible 20 colors when putting text on the detected object boxes. And the image reading starts here on line 29. By using CV2's imRead method, we just read our image into a variable which is called org. This is, of course, a math type object. We get the width and the height of the original image here, and then we define a new object called img2 of math type. Because the mobile net SSD requires us to reduce the size of the image to 300 pixels by 300 pixels. We just happen to resize our image, original image, and place the resized image in img2 variable. One of the constraints of this framework is also the scaling factor, which needs to be 0.007843, and also the mean subtraction value is defined here with a scalar object, and all the parameters are 127.5. So this is the mean subtraction value. If you recall, the numbers were different in the object classification application. And then we call the CVDNN's blob from image method as before, placing all the required parameters, our resized image, scale factor, and again, we need to use that resizing here also, and mean subtraction value, and swap blue and red true, cropping false. And then we call the CVDNN's readNet from Caffe method with these parameters in order to create our network object. And here we use the blob object. So we place this as a parameter in the setInput method of the net object. We then do a forward pass, which passes the blob object through all the network layers. And we receive a math type object, which we call detection. This detection object is a multi-dimensional object. Actually, it has got 4 different axes. We need to convert this object into a 2-dimensional array. Using the reshape method of the CV2 class, in the end, what we are going to have is a 2-dimensional matrix with n rows and 7 columns, with rows indicating the objects detected and columns giving us information about the object detected. Having converted our detection object into a 2-dimensional P object on this line 55, what we have to do now is to iterate over the rows of the P object and get each detected object one by one. And that's why we have a for next loop starting on line 66. At this point, let us have a look at a slide in order to see which column position contains what information in each row. In this slide, I have drawn a table representing our 2-dimensional P object. Each row in this table represents an object detected. And at each row, the column with index number 1 holds the class ID of the object which has been detected. The column index number 2 will tell us the confidence or the probability that the object is what it is claimed to be by the class ID information. This probability value is between 0 and 1. So a value close to 1 indicates a very high probability that the object is what it is claimed to be. And you can easily guess what a value close to 0 means. During iteration, we compare this value with a threshold value. If the value obtained is over that threshold, we confidently say that this is an object that we need to take into account. If not, we discard it. In our application, we'll be setting this threshold value at 0.5. You can certainly play around with this number in your experiments, but as you decrease its level lower than 0.5 or so, you may get an object detected more than once or may detect a real smaller object in the background. The columns 3, 4, 5, and 6 will give us the normalized coordinates of the bounding box of the object detected or its position. When I say coordinates, they are the top left and bottom right x and y coordinates of the box that surrounds the object. With this information, we can easily draw a rectangle and see the object's bounding box. However, before doing that, we need to multiply each coordinate value extracted from the columns by the width and height respectively of the input image to get the real scale coordinates, as the coordinates obtained are normalized and therefore reduced numbers. Once we know the class ID of the object, then it's a matter of inserting that to the labels array in our code to extract the corresponding name of the object. So much for the background information. Let us see now how we have coded to get these values. Here is the line 69, to get the probability or confidence level from index position 2. Then the comparison of this confidence value with the threshold value, which is set initially to 0.5. If the confidence level is over 0.5, then these lines are used to extract the coordinate values as explained in the slide a moment ago. The rest here is business as usual. Extraction of the object name from the labels array using the class ID found and drawing the bounding box on the original image. We also prepare a text here to place on the upper border of each bounding box to show the object name and confidence level. We then display our original image using a window object here. So in our first trial, we are going to be using this dog bicycle car image. So let us run this project now. So the bounding boxes show that we have detected 3 objects. One, dog object with 99.72% confidence level, bicycle 99.63, and car 96.46. And the time taken for this detection was 323 milliseconds. If you have a look at the number of rows here, we notice that we have actually detected 4 objects in the first place, but we have got only 3 drawn on the image. Why is that so? One of them must have been eliminated by our threshold level. So there was also an object detected with the confidence level of 0.35, and I wonder what that object is. So let us go back to our code and change the threshold value to something lower than 0.35 and see what that object is. Let me just change it to 0.34, save it, and run it again. What do we see now? Well, we see that we have the rear side of the bicycle detected as another bicycle. That's a false detection, of course. So reducing the threshold value may sometimes result in false detections. That's not always the case, as we'll see in the next image. So let's do our trial once more with another image. I'm going to change that value back to 0.50, and this time the image name will be doghorserider.jpg. Let me save this again and start debugging. Well, this time we have 4 objects. One here, car with 99.06%, and a dog with 95.74%, a horse with 99.94%, and a person with 93.38% confidence level. But if we look at the console figures, we see that we've got 5 rows. So 5 objects must have been detected, and 1 is eliminated or filtered out. That object which was eliminated has the confidence level of 25%. So I wonder what might that be. Let's change the threshold value to 0.24 and observe it. Wow, there's another person detected here in the background, and the detection time in this case was 256 milliseconds. So after these 2 trials, we can confidently say that our object detection implementation is working well, detecting objects with high accuracy and speed even on CPU. So can you imagine what the detection times might have been had we been doing this work on GPU? Well, that concludes this section. In the next section, we'll convert this application into one which does the detection in real time from images that come from a webcam. So see you in the next section.